Unit 3, Section 1, Equivalence Relations. Section Objectives. By the end of this session, the students will be able to 1. Determine whether or not a relation is an equivalence relation, and 2. Prove that relations are equivalent. Equivalence relation. We want to look at some few examples of equivalence relation. And the first one is, if you let R be the relation defined on the set of positive integers by the relation A is related to B, if and only if A is equal to B. And we are to prove that the relation R is an equivalence relation. Now, how do we prove this? For us to prove that the relation is an equivalence relation, the relation must satisfy 3 conditions. And these conditions are: 1. The relation must be reflexive. 2. The relation must be symmetric. And 3. The relation must be transitive. So now let's look at the reflexive condition. If we assume or we take x to belong to a set of positive integers, then the equality sign in the equation, that is A is equal to B, becomes x is equal to x, which means that x is related to x. This is because if x is related to x, then meaning x takes the place of A and x takes the place of B, and which gives the x is equal to x, and hence the relation is reflexive. Now, for the relation to be symmetric, then our x is related to y should be equal to y is related to x. Now, if x is related to y, then the relation given, then our x is equal to y, which means y is equal to x. The y is equal to x means that y is related to x. And since x is related to y is equal to y is related to x, then we can conclude that the relation is symmetric. Now, to prove that the relation is transitive, we assume or we take x, y, and z to belong to the positive integers. If that is it, then our x is related to y and y is related to z. If x is related to y and y is related to z, then we can say that x is equal to y and x is equal to z. If x is the same as y and y is z, then we can say x is equal to z. So, by the relation given x is related to z, then this proves that the relation is transitive. Now, since the relation meets all these conditions, the relation is reflexive, the relation is symmetric, and the relation is transitive. Therefore, we can say that the relation is an equivalence relation. Equivalence relation. Example 2. Define the relation R on Z by A is related to B if and only if A plus B is even. Show that the relation R is an equivalence relation on a set of integers Z. Now, to show that the relation R is an equivalence relation, we must prove that the relation is reflexive, it is symmetric, and it is transitive. Now, let us show that the relation is reflexive. For the relation to be reflexive, then A should be relating to itself A. And if A is relating to itself A, and we take A to be an integer, then in A relating to B, which gives A plus B, the A takes the place of B. Hence, A relating to itself A gives A plus A, which is 2A. And it is even because since A is an integer, If you multiply it by 2, it gives an integer, which is even. Now, A is related to itself. So we can conclude that the relation R is reflexive. Now, to prove that or to show that the relation R is symmetric, we let A, B be integers. And if A, B are integers, then A relating to B should be equal to B relating to A. Now, A plus B is even, but for B relating to A, the B plus A should also be even. Now, if A plus B is equal to B plus A, which are both even, then we can conclude that B relating to A is symmetric. Hence, the relation R is symmetric. To prove that the relation R is transitive, we take A, B, C as integers and assume that A relating to B and B relating to C, which implies A relates to C. Now for A relating to B, then our A plus B should give us an even integer. So if K belongs to set of integers, then we multiply it by 2, which gives A plus B is equal to 2, which is an even integer. Also, for B relating to C, then our B plus C is equal to 2L, where our L there belongs to set of integers. Now, since our interest is in A relates to C, then we make A the subject in the first equation, and that gives A equals 2K minus B. And also we make C the subject in the second equation, and that gives C equals 2L minus B. Now, for A relating to C, it means A takes the place of itself A, and C now takes the place of B. Hence, our A plus C is equal to then 2K plus 2L minus B minus B, which gives minus 2B. But note that our A plus B is the same as 2K, and our 2L is the same as B plus C, then minus 2B. Now, 2 is a common factor, so it's factored out. If 2 is factored out and K plus L minus B belongs to set of integers, if we multiply it by 2, it will give us an even integer, which means that A plus C is even. Hence, we can say that our relation A relating to C is transitive. Hence, R is transitive. Now, since the relation satisfies the three conditions, that is, it's reflexive, it is symmetric, and it is transitive, we can conclude that the relation is an equivalence relation. Equivalence relations. Example 3. Let B is equal to R minus the set with an element 0. Define the relation R on B by A is related to B if and only if AB is greater than 0. Show that R is an equivalence relation on B. Now, for us to show that the relation R is an equivalence relation on B, we must show that the relation R is reflexive, it is symmetric, and it is transitive. Now let us show that the relation is reflexive. When we take X to be a member of B, then for the relation to be reflexive, X should relate to itself. If X is relating to itself, meaning we have X, R, X. So X takes the place of A, X takes the place of B. So that we have X, R, X equals X times X, which is X squared, which is greater than 0. And we can say that X is related to X for all X belongs to the set B. Then we can conclude that the relation R is reflexive. Now, to show that the relation is symmetric, we take X, Y to belong to B. And our X is relating to Y, which means that X takes the place of A, Y takes the place of B, which gives XY greater than 0. And also, Y should be related to X. And if Y is relating to X, then it means we have Y Rx is equal to Yx. And since X relating to Y must be equal to Y is relating to X, then we have Xy is equal to Yx. And Yx is greater than 0. And we can conclude that the relation R is symmetric. We look at the transitive aspects in the next slide. We want to show that the relation R is transitive. Now, for the relation to be transitive, we take X, Y, Z to belong to the set B, so that our X related to Y and Y is related to Z, which implies that X is relating to Z. Now, if X is related to Y, then our XY is greater than 0. And if Y is relating to Z, then our YZ is greater than 0. Now, if X is greater than 0, then since XY is greater than 0, Y must be greater than 0. This is because if X is greater than 0 and Y is less than 0, if we do the multiplication, it gives negative, which is not greater than 0. So that is why Y must be greater than 0. Now, if Y is greater than 0, then our YZ must be greater than 0. If YZ is greater than 0, it means Z must be greater than 0. And this is because if Y is greater than 0, which means it is positive, but Z is less than 0, which means it's negative, the product will give negative, which will not be greater than 0. That is why Z must be greater than 0. Then we can say since X is greater than 0 and Z is greater than 0, then it can follow that our XZ is greater than 0. And that is X is relating to Z. That is the case for X is greater than 0. So now let us look for the case of X is less than 0. When X is less than 0 and our XY is greater than 0, then it implies that Y must be less than 0. This is because if X is less than 0, which means X is negative, Y cannot be positive. Y should be negative so that when we multiply XY, the result will be positive, which should be greater than 0. Then since Y is less than 0 and YZ is greater than 0, then it implies that Z must equally be less than 0. And this is because if y is less than 0 and z is not less than 0, the product will not give positive. It will give negative. So that is why the z must be less than 0, so that when we find the product of y and z, it should be positive, which should be greater than 0. Now, since x is less than 0 and z is less than 0, then we can say that our xz is greater than 0, and that is x is related to z, which implies that our relation R is transitive. Now, since from the previous slide, the relation is reflexive, it is symmetric, and it is transitive here, we can conclude that the relation R is an equivalence relation.